molar mass. This is old, we already know how to do it, you might as well not even write that down. But some people in the room still are not very comfortable calculating molar mass. Calculating mass percent. So I'm going to stop here. Maybe like write down what slide I'm pointing to or something. I don't want to write down everything, that'll take a long time. We are making a really specific study guide right now. Calculating, there we go. Percent composition. That one will definitely be on there. We did this on the quiz,
Is mass percent
and we said that this
composition
is one of the questions from chapter 6. So here's where you need to know how to name, or else you won't be able to calculate it correctly. Let's say I ask you to calculate the percent composition of iron 3 nitrate. And that's all I tell you, iron 3 nitrate. You have to know what that looks like. It looks like this. So you need the polyatomics. You need to know how to name. I would say for probably 30% of the final, you need to know how to name in order to do the question. So this would be like, what's the percent composition of nitrogen in iron 3 nitrate? So you would add up the mass of 3 nitrogen divided by the total mass of iron 3 nitrate times 100, and that's percent composition. And then the other question from this chapter is the long one going from percent composition into molecular formula. That's a calculation, that's a whole process. This is the difference between empirical and molecular formula. And for this, you gotta go from percent composition to empirical formula to molecular formula. Here's the process. This was a long time ago we did this. These are good practice problems. And I want to say we've done both of these. There's N. Here's a good practice problem, and it's worked out for you here. So if you can do this one, you're chilling. In fact, this one was on the quiz. C20, H40. That's exactly the same one that was on the quiz. Same numbers, words, and everything. And then, of course, we always need to know how to go from grams to moles to number of things. Let's make another map of how all the different ways we have learned this semester to get into moles. Why do we always want to get into moles? Because this is the way that we convert mathematically from one compound to the next. So we always have to get into moles because we're always asked to figure out, if I have this much stuff, how much of that much stuff can I make, or how much of that much stuff do I need? So to get into moles of one compound, we can use, we can go from grams to moles with molar mass, right? This is repetitive for those of you that are caught up in life. That's old news. And then we can go from molarity to moles with the volume.
Almost.
Some of us are finally getting comfortable with that, but probably we're still pretty shaky there. You don't like that one. That's capital M. You multiply it by liters, and you get moles. And then the last piece that we added in was using the ideal gas law. This is our last way to get into moles. Moles is N. And then if we want to go from moles of one molecule into moles of another, which we always have to do this, we use the mole ratio. And we're still a little shaky on that. Mole ratio comes from the balanced chemical equation. And that's basically what this whole chapter is about, is you understanding stoichiometry and the mole ratio. 6, that's pretty much it. We've got calculating percent composition. We've got calculating molecular formula from percent composition. And then I'll add one more piece to this. Grams to moles to number of things. That's of course Avogadro's number. And let's make sure we are very certain what that number is and what it represents. 6.022 times 10 to the 23 things is equivalent to 1